So it might be it today, as I'm hearing. I don't know. There's normally more people here, right? A couple? Not a lot? Okay. I guess. Put this over here. Get started. All right, that's okay. I guess we'll get started. So, hi. My name is Christian Hubicki. I am a professor here at, in the mechanical engineering department here at the College of Engineering. And my specialty is in robotics, particularly bipedal robots that walk around on two legs. And I investigate things from robots to also running ostriches and beyond. That's sort of like the overall overview talk I'm going to give you today. The way I look at it is that this is sort of like a vignettes of bipedal locomotion, okay? Specifically bipedal locomotion. 4 of them. I'm going to kind of take you through a little overview today. And they range pretty wildly from this bipedal robot called Duris with wearing sneakers, to these ostrich experiments here that we analyzed, to this little tiny robot about yay tall that's jumping on sand, and this very interesting looking robot called Ostriches, which we got running outside at the stadium at Oregon State University. So, and very specifically, these have very particular research aims to each of these robotics projects. This Duris robot, D-U-R-U-S, it's specifically a project about walking with a robot with minimal energy costs in order to reduce the amount of drain on the battery on board. That's what that project is about. This project on birds, cursorial birds, which, by the way, anyone know what cursorial means? It means ground running, if you can read that, ground running birds. So think ostriches, several kinds of quail, turkeys, those sorts of things. And this is about understanding what do animals care about when they're running around. What are their objectives of their control? That's that particular project aim. Also, this project here about this jumper is about granular terrain. Granular being like sand. And we call this project terrain-aware locomotion, where you have the ability to control some machine, but it's aware of what it's stepping on as part of its control algorithms. And finally, this Ostriches robot is very interesting, and it's about agile and robust walking and running, as opposed to low energy cost walking alone. So each of these has its own sort of place in sort of the bipedal spectrum of research. So, but also, there's one big overarching connecting methodology that I use called optimal control. It's applied optimal control specifically. Sometimes it's called trajectory optimization in the literature. Okay? So this is a tool set that sort of unifies all these projects as I've approached them. All right? And specifically, I apply these on robots that we have that we call that are compliant. Anyone know what I mean by compliant? They stretch. They're not rigid. They bend. That makes control more difficult. So you can also see these as not as vignettes of just bipedal locomotion, but also vignettes of optimal control. So here at this Duris robot, we apply optimal control to broaden existing legged control schemes. That was my the general thrust of that research project. We use some method. It sounds fancy. It's called hybrid zero dynamics, but it's not quite as fancy as you might fear. It's actually very cool. So with these cursorial ground-running birds, we're using optimal control methods to figure out what they care about. We are taking a mathematical model of birds, applying optimal control to it with a known objective, say minimize energy costs, and see if that replicates how birds actually run. And in doing so, trying to infer what birds care about. This granular terrain, this is about making terrain models for the ground that are actually computationally efficient enough to run inside of an optimization, which can be quite a challenge. We use both sort of models of the ground that are based on physics, but also based on machine learning. And finally, this Ostriches robot, this is about using optimization to come up with components of some grander controller that can do lots of things. And I call this sort of optimization-inspired control. So I jumped straight into it. By the way, I'm going to keep you oriented here down in the bottom left-hand corner. You can see which part of the talk you're in, so you don't get lost. Right? So you're probably thinking, Christian, you jumped straight into this. Why are you talking about robots with legs at all? Well, because they're cool. For what? Legs are cool. Right? So here's an example. What's embedded in this question is why not wheels? Wheels are great in nominal circumstances, but sometimes things in extreme circumstances, legs can be very useful. This guy, this Spider-Man-like fellow, was very happy that he survived thanks to his ability to do intermittent contact with his legs. So that's an extreme example. More generally, though, legs are great for getting around in rough terrain. So like this, sort of like hiking up through thickets and things like that, where you can sort of change your contact points and move through. Also, you can get up over large obstacles with a relatively small form factor. I can stand in a fairly small space and get around just fine, and still be able to step up large objects. These are little reasons. I find it more interesting also because I think it's really important for understanding human legs. All right, you have prosthetics that need to be able to interact with people and, in a way that makes them walk better. And understanding the mechanics of how legs move and how to control them is useful for that, as well as exoskeletons and rehabilitative robotics for having people basically who've had spinal cord injuries basically relearn how to walk by having machines take them through the motions. I think that's a pretty interesting challenge as well. So let's look at some robots, okay? So who's seen Asimo? This robot up here, who's seen it? Okay, very famous robot. It walks around, it serves tea, the usual. It also has a very awkward interaction with this woman right here, where he figures out which way to walk, and he goes that way. Okay, so very human-like in terms of my interactions with people. Also, you have Big Dog, right? This very famous robot took this kick back in 2006. Amazing machine, right? That's astonishing that it can do that. Why? So is this like a solved problem? Sort of what we get at, and the answer is really no, and one giant reason, and that's the energy economy of these machines. Here we have a person, and here we have Asimo, all right? And we can actually measure how much energy it takes for a person to walk. It's something called a cost of transport, and same with a robot. It's the amount of energy it takes to walk per unit mass and gravity, which is weight, per unit distance. All the units cancel out, gives you a nice non-dimensional number, which is something called cost of transport. The higher it is, the more it costs to walk. And the lower it is, the more efficient you are. So for humans, you can actually measure this with metabolic cost using O2 masks over their face when they're walking on a treadmill. And their cost of transport is 0.2, which is quite a low number. Asimo, about 3.2, 16 times as much as a person. So, so a lot more. Big Dog, I'll give you a hint, it runs on gasoline. So how much more do you think energy it takes for a Big Dog to walk than a person, based upon estimates? I'll take guesses. 20 times, very close, 75. 75. So it's an amazing machine. Do not get me wrong, but it comes at a cost in a way that's actually sort of infeasible. Asimo would typically run out of batteries by most estimates, because they don't tell us, within about a half hour to hour of use. So that's a real limiting factor. Also, it just tells us we're doing it wrong. We're doing like locomotion wrong. If I can do this, haphazardly me tripping around the stage here, orders of magnitude better than robots. We have a lot more to learn about legged locomotion. Atlas, people have seen this amazing machine, and the answer is we don't really know. There's not enough information out there to know how much energy it takes Atlas to walk, but there is some hints that it's as much as 100 times based upon certain DARPA BAAs. So again, amazing machine, but it costs a lot, all right? So how do people typically make robots walk with two legs? Oh, there's this method, it's called zero moment point walking, or ZMP. A lot of times, if you kind of just scour YouTube looking for any robot that's kind of moving around in a way that's a little bit on the slow side, they're probably using a method based upon zero moment point walking. And the premise is very simple, all right? If I have my body in a static place, and my center of mass is over my foot, I am not tipping over, and therefore I am not falling. There is no net reaction torque. And then if I put my other foot down, I can then shift my center of mass along this sort of polygon of support until it's over this foot, lift it up, and keep going. Rinse and repeat. That's a very common way. Now I encourage you, when no one is looking, to try walking in this fashion. You will get tired very quickly. You will also look quite silly. And we don't walk this way for good reason. We kind of just stick our foot out and fall and catch ourselves, as opposed to very carefully controlling our center of mass motion to be over our feet. And further, for robots, walking this way requires a lot of assumptions about your machine. One is that it's fully rigid, and you have full actuation of all your joints. You have a motor at every single joint on your robot. You know, and you can do that, but this actually impacts the way that the actual machine functions. What we call passive dynamics. That if the machine is off, how does it behave? And whereas, and I'll show you a visual example soon, but if you have motors and gearboxes at every joint, your machine is going to be quite rigid. And I'll show you what I mean. So let me talk, what are passive dynamics? So it's not a really great definition out there, but there is one on Wikipedia that I happen to like, which says passive dynamics refers to the dynamical behavior of actuators, robots, or organisms when not drawing energy from a supply, when the robot is off, when the animal is dead, for instance. Okay, I happen to like this definition, but I am biased because I did write it. So moving on. So what does that mean? So here you have Asimo in a video that I swear is not to make fun of it, but Asimo's going to fall down these stairs, okay, because of a computer crash. And when it falls like a rock. All right, that's the key fact here, is that when it falls, it just the limbs aren't flying around, the legs aren't flipping around. That's what I would probably be doing if I were falling. So you can get a glimpse into what Asimo's passive dynamics are like. They're very rigid. Every single motion has to be carefully controlled as a consequence. And you can imagine if you had to move around like this on a daily basis, you would be very tired. It takes a lot of energy. So contrast that with an animal. This is a gibbon at a zoo, just kind of zipping around on the structure. It's so fluid, so natural. It's not tightly controlled at every single joint. It's just kind of going with it. It's very agile as a consequence. Further, this is one of my favorite videos here. This is a rainbow trout. And it is swimming in a stream in an experiment. And you can see it starts to swim upstream behind that rock. All right? Now, you might say, Christian, I've heard that fish swim upstream before. That's true. But this fish is dead. This dead fish is being buffeted around by the vortex wakes of the water and being propelled upstream without any control or any energy input from the fish itself. All the energy is coming from the water. And in a way that it just goes upstream. Isn't that amazing? So it takes no brains at all. It took no control at all. And it can do stuff. So talk about efficient locomotion. All right? So there are people that have essentially taken this idea of passive dynamics to an extreme, where they try to build robots that rely entirely on passive dynamics in order to try to walk. So this gentleman here, Tad McGear, back in 1990 with his old video on VHS, made this robot. It's basically an erector set. There's no motors, there's no computers, there's no battery, there's no nothing on it. It's just a couple of joints. And what he's going to do is he's going to push it down a very shallow slope. Like that's the horizontal, that's the slope it's walking on. So its energy source is this tiny little incline. And he's going to give it a push. And it walks. Not very long, but it walks. The concept is there that he was able to take this machine that's based upon a very simple set of dynamics here, which is the dynamics of a pendulum, and make something that walks with almost no issue and no energy input other than this slight shallow slope. And I would say it's much more natural looking than something like Asimo and how it walks. So in my research, I use a different kind of model. Instead of that pendulum that he used, which was basically just vaulting one foot over the other, boom, 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 falling from step to step, I use a slightly different model in all my research, which is this spring-loaded model. It's basically like a pogo stick. It's called the spring mass model. Some people call it the spring-loaded inverted pendulum. But it's very simple. It's just got a math model that has just a point mass on the body. The leg is just a spring that weighs nothing, nice linear spring. And as a consequence, it's just this very efficient bounding-like locomotion. And I use that as a basis for both the robots I help design and the robots I control in order to make our robots more efficient and more agile. So just in contrast, he built a robot based upon this simple pendulum model. I'm building one around this sort of pogo stick-like model. Okay? So, and people have used this to analyze the biomechanics, to analyze the locomotion of people and animals for years, not just for inspiration for robots. You can make this model walk if you have two legs. You simulate it walking, and you can measure how much force it puts up against the ground. If you were to have like a real-time bathroom scale and we're walking on it, it would have over time this little double hump profile. And when it runs, it has this single hump profile, basically bouncing along. Okay? And the reason that's kind of interesting is that when you look at humans, they do the same thing. They have this sort of this series of forces dictates the way that the center of mass, the whole body, moves of this very complicated thing that is a human in this very simple model. All right? And not just people. People, we also analyze cockroaches, ghost crabs, which are adorable, and dogs, and all kinds of creatures with this model that even though you might have many, many legs, the center of mass tends to bounce along like the simple mass on a spring. It's been studied for decades now. So in my research, I try to build this sort of spring mass dynamics into the machines that I'm controlling, and also into the animals into the way we analyze animals, like this ostrich. Okay, and even this little jumping robot has a little spring in there. Okay, there's a spring in the foot of this robot. There's a this whole giant leg acts like a spring on Atreus. That's sort of the premise of a lot of my research. So the problem is when you do this, when you start putting flexible things in your robot, it gets harder to control. If you were to go to a factory robot, per se, something that's going to assemble cars together and welding stuff, and you were going to go try to move that robot around, it's going to be rigid. And there's a lot of good reasons for that, because when the robot is rigid and fully actuated with every motor, every joint, the control problem is much easier. When things are flopping around, there's all kinds of crazy dynamics. I mean, this is a kinematics course. Am I understanding? So yeah, so I mean, imagine the kinematics of something that's flopping around. I mean, it's not a kinematics problem. It's not a dynamics problem, right? So we think that there's benefits to putting these springs in there, but it makes our job to control people harder, all right? So the way that we go about this is we do a lot of optimization of our control, nonlinear optimization to satisfy our control problem. And just very basically, optimizations involve minimizing some objective function subject to a bunch of constraints. And in the context of these control problems, it's like minimize the amount of energy cost for this robot to walk, subject to the constraint that it is walking steady. And those constraints are important, right? Because what's the most energetically efficient way to behave if I don't give it those constraints? Fall to the ground, right? So these constrained optimization methods are what we use to come up with our control policies. And we use something called trajectory optimization. I'll go through that very briefly, all right? Just a little bit of background on what that means. So if you're trying to create an optimization problem to figure out how to control a machine, the simplest way to try to do it is something called a single shooting formulation. And it's simple, okay? Let's say you have your state over time. People have taken some kind of controls courses here. Your state space controls. And you have some control input over time as well. And you're trying to optimize your input, your control input over time, such that your state hits this target. Okay? So, and the way you typically go about this is adding a bunch of variables here in discrete time. Boom, 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 boom. Where you can sort of ride each of these variables up and down, say a little bit more, less control input. And you sort of connect them via some spline. And you say, so yeah, and you have some definition of how long it will take to complete the maneuver. And then you have some initial state that you can choose. These are all free variables that you can change. And then when you have all these variables set, you simulate. You shoot. Boom. And you see how well you did. Well, we missed. Not a surprise. This seems pretty random. It'd be remarkable if this succeeded in hitting our target. And we call that difference there a defect. All right? So we create an optimization problem where we say we minimize some objective subject to the constraint that this defect is 0. So we give this to some optimization algorithm, something like a sequential quadratic programming, an interior point method. You can use any kinds of jargon that you want. And what it will do is it'll kind of search around the space for all the ways that it can jiggle around these variables. For instance, it might take this variable here and then try bumping it up to here and see what happens. All right? Then it'll shoot again and simulate and see how well it did. And then it'll miss again and try to find a way to get closer and closer and closer. The problem that's a little technical to explain is that because when you jiggle around this variable here, it has to go through all these nonlinear dynamics up here. a small change here can have drastic nonlinear changes by the time it gets to the end of the shot. And so when the optimization is trying to figure out what the heck is going on, it gets confused. And often it'll say, I can't find a solution. I don't know how to navigate along all these spaces of variables I can jiggle around to find an answer. So there are better ways to do this optimization. There's something called multiple shooting. Very clever, single, multiple. They're clever people who name these things. So you take the same setup here, where you have all these variables aligned along this along this sort of timescape here. And you have the same variable up here for your initial state. And instead of shooting all the way to this target, you shoot a little bit forward, OK? Then you're going to add another variable right here. And then you're going to which is a free variable that you can control. And you're going to shoot forward again. Then you're going to do it a whole bunch of times, all these multiple shots. And the reason we try this is like, well, maybe this one big long shot has huge nonlinear effects. But the shorter that shot is, the more we approach local linearity. And so as a result, there's a nice linear relationship between how you might change this variable. So anyway, how you might change this variable right here and how it affects just this one little shot. All right? So we still have our defect constraint that we want to drive to 0. But you might realize there's something horribly wrong with what I've just done in that these lines don't connect. This is a state space system where states are bump, 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 jumping all over the place. OK? So it makes no sense. So we need more defect constraints all over the place. We have to drive this to 0, this to 0, this to 0, et cetera. All right? But the nice thing now, as I said, is if you change this one variable a little bit and then reshoot, it's a relatively linear change. And the same thing with all these other variables here. So even though it's a much bigger problem that you're trying to solve with many more variables and many more constraints, it's actually easier for the optimization to come up with a solution. Isn't that interesting? People have used this for some simulated humanoid studies in the past. But there's an even better way to do this than multiple shooting, something called direct collocation. Take the same problem setup, all right? And where you have all of your inputs, you have your initial state, and you have all those individual variables that you have control over along the way. And instead of doing any shooting by simulating your system, you just connect all of your points via some kind of spline. Linear spline, quadratic spline, cubic spline, choose your spline, I don't care. All right? So basically just connecting the dots. Then what we do is we look at the center of one of those splines. And that's called a collocation point. All right? And we look at the tangent line at that point on the spline. Now, what is that tangent line in the context of this system where we have states and time? It's x dot. It's x over time. X dot is equal to the dynamics of our system, if you've ever taken nonlinear dynamics, which is a function that you know from your equations of motion. And essentially, you have a constraint that says the slope of that line needs to equal your dynamical equations of motion. And that's your new defect constraint. And you apply that to all of these little collocation point splines, all right? To each of these little tangent lines. Now, why is that more interesting? Well, this is normally a closed form equation. That's your equations of motion. Either you did it with Newton's laws, or you put them into some big Mathematica package that spits out your equations of motion. You don't have to do any iterative solving of your dynamics to do an integration step. All right? For each of these, you have a simple closed form equation describing all of your constraints, which means it actually makes the optimization problem super easy to solve because you get not only a closed form expression for each of your constraints, it's super fast to evaluate, but I can also take all the derivatives analytically. So not only when I'm navigating the space, I don't have to try different points all around the place to figure out where I'm going. I know at this point not only what the value of my objective is in constraints, I also know the gradient, just analytically, super fast. So that makes things work really quickly. Anyway, that's trajectory optimization in a nutshell. And use it for problems like making this quintuple pendulum on a cart swing from the bottom to the top. You have this cart. It's kind of a benchmark problem. You have to swing it around in such a way so that it swings up and balances. And this takes about 30 seconds to solve with these methods, which is insanely fast. Just get a sense of the complexity that you can solve with these methods. This is a big upple pendulum on a cart. This is basically 20 links on a cart, and it's like a sausage swinging around. It's an incredibly hard, like many thousands of variable optimal control problem. Solved. So we use that for robots like this Durus robot, okay? With tons of links running around, kind of swinging around, in order to come up with an efficient way to make it walk. So this is the Durus robot. This was one of its earlier control iterations when we took it to the DARPA Robotics Challenge in Pomona, California in 2015, just to show that we could actually get the machine to walk at all. It was designed as part of a program to make a robot that walks with 5% of the energy cost of the Atlas robot, which we were told was 100 times as much as a human to walk. So if you do math, that's like we have to make it 5 times worse than a person. And if you do math, 0.2, 5% times 100. So anyway, so 5 times worse than a person, which is a huge milestone to hit. It was built in collaboration with Oregon State University, where I did my PhD, Amber Lab, which is now at Caltech, which I did my postdoc, and SRI International, which is a corporation out near Palo Alto. And it has all kinds of mechanical features that make it very mechanically efficient, such as cycloid gearboxes. They're very easily back-drivable gearboxes that don't have a lot of friction, so they operate really nicely. And also, it's got these springs here, very soft. There's like a suspension for your car. Every time you hit the ground, there's a little bit of bounce. So all the energy that you would always normally have in the system that would normally hit the ground and hit a plastic impact, all that energy that ordinarily would be lost, some of it is recovered by the springs. But again, that makes the control problem more difficult. So at the DARPA Robotics Challenge, you might have seen some hysterical videos of robots falling down on YouTube at some point. It was probably from this competition where people took these robots, these humanoid robots, and had them walk around and have to go into a simulated nuclear disaster and like shut off a valve. Like, oh, shut off the valve before the plant melts down. Oh, no. And it has to do that. It has like an hour to do it. And because they gave them such time, and they needed to be very careful, they took these very ZMP, zero moment point-based methods to walk around, and as they rightly should have. And they did all this great algorithmic work in order to be able to plan through its environment and pick up objects and pick up a power drill and have it drill through a wall and stuff. So very neat. But it wouldn't work for us because our system is not rigid. It's very, very compliant with all these very soft springs. So we have to use a method that's something called hybrid zero dynamics, which is a control method that has existed in simpler machines that just walk around in a circle very effectively there. We had to expand it to something that was more like a humanoid, which has a lot more degrees of freedom, a lot more joints, and also has to walk around in 3D. And that's harder. So the challenge for us was to be able to use the methods of this control method called hybrid zero dynamics, which involves some kind of optimization, and make the optimization scalable to the size of humanoids. And for that, we use that direct collocation scheme I talked about. So the general process was we have our model of our robot. We put it through some giant mathematical package to give us the equations of motion, also a few supplementary equations that come from the hybrid zero dynamics control framework, and shove that all into one giant optimization problem using direct collocation. And on the other side, we hope we get 3D dynamic walking, not static walking, very dynamic walking that's hopefully efficient. So just very super quick primer. We use this method called partial hybrid zero dynamics. I don't have time to go into any detail on this, but it's really interesting. And essentially, the control concept is that you have this massive state space for your 26 degree of freedom robot. So it's like 52 states. And it's a kind of a mathematical way to collapse it down to just a few. So that way, the control, the dynamics of the system actually are much simpler and easy to analyze. That's the framework we're working within. But the key is that it requires us to define these equations. They're called outputs. Actually, who's taken controls 1? Controls. Remember, thank you. So people, you have your state space equations. So you'll have your x dot is equal to ax plus bu, and then you'll have your output, which is y is equal to cx plus du. That y is an output. It's just this is an output y in a nonlinear dynamics context, in a nonlinear controls context, just to give you some basics as to where it comes from. All right? But the point was we have to define these output functions as part of the control method, and we have to optimize for them. And we're looking for these parameters right here, which are these alpha values. And that's what pops out of the optimization. that we're going to need to actually control our robot. Okay? That's what we're going to get out of the optimization. So we used that direct collocation approach that I talked about. This is just a rehash of what I showed in great detail with splines and tangent lines and all that. And we run a giant optimization problem, which has about 10,000 variables for this machine to come up with a way for it to walk efficiently, at least as efficiently as you can. So particularly, we say we want this 23 degree of freedom robot, which didn't have arms at the time, still doesn't. It's 23 degrees of freedom with only that stuff. So that's what? 46 states, actually, plus the original 6. It's 52 states system. It's a huge system for robotics. While minimizing, have it walk, while minimizing energy costs. And we use the specific cost of transport, that COT, that number for people. That's the thing we're trying to minimize, that exact number. And we started off doing flat-footed walking, but eventually we actually got it to walk in a more heel-to-toe fashion, as you see here. Anyway, so we actually run it through an optimization in MATLAB. Who's used MATLAB? Everybody? Yes, thank you very much. So yeah, just MATLAB. All right, there's a couple other packages involved, but we run it through. We use MATLAB to formulate the problem, and we solve it. It takes about 10 minutes to come up with a solution for a controller, which is actually really fast. And most importantly, it comes up with a solution. It doesn't get stuck and give us no answer. And what it gives us, in effect, for this robot, is a series of joint trajectories. That's what pops out of sort of the hybrid aerodynamics formulation. It's a bunch of joint trajectories for us to follow for each of these joints that should make it walk. So when we do that, put it on a giant treadmill, we have this, the robot walking. All right? So we have it walking from heel to toe, which we're very pleased about. That actually makes the control problem even harder. This is me at 6 in the morning after a long night of testing. So we eventually got this working. Things kept breaking. But we were very pleased. And you might be wondering, where do you get robot shoes? Well, the answer is the shoe store. You take your robot foot, put it on the sizer, and they size it up for you. This guy was a complete professional, by the way. He was not fazed by the fact I was bringing in a robot foot for a shoe. But I was a little offended, actually. He was more impressed. But he did a great job. So we got shoes that fit the robot. And you can see here's my colleague Jake walking behind it. So we're very pleased with that. And now I wish I could tell you that was the whole story behind the controller, that it all just popped out magically out of the mathematics and the optimization and it worked perfectly. It doesn't quite work like that in robotics. It's always a little bit extra sometimes you have to do because it's such a hard problem. It's like a nonlinear, hybrid dynamical, high degree of freedom, under-actuated control problem. A nightmare. We got really close. We had to add this extra little bit of control on top of the controller that you saw, which is really simple, which basically came down to when you're falling to the side, kick your foot out a little bit more. After all that math, we have this tiny little controller at the end that helped just push it over the edge to something that would walk. So this very simple sort of like the heuristic-based controller that we had to add in order to make sure that it just kept staying up just right. And just put a pin in that because that'll show up a little bit later. Okay? So this old chart, how did we do? We did it. We got 5 times worse than a person, which is the best it's ever been for a humanoid robot. So, but it paid off. So we did much better than the state of the art, so we're very proud of that. But you might know, and also that same method that I showed, it's not just for walking with that particular robot. We did it with this other humanoid robot with arms. Also this robot here that was running on a treadmill. So it's all the same. It's an extensible methodology that you sort of just plug in your robot and give it a task, i.e. running, and as long as the machine is physically capable of doing it, it should do it. Again, there's always little tweaks you have to do when you're all done, but it's fairly extensible. So, but you'll notice that that's all about walking on flat ground. Well, if the whole world were flat ground, why the heck are we doing with walking robots? So what about rough terrain? What happens when the terrain is like jagged and has weird geometries? What do we do? Right now we're optimizing for energy costs. Should you optimize for something else when you're going over rough terrain? Is there some mix of objectives that you want? It's not just energy. Maybe it's like, making sure you don't get too far over and not fall over. So question is, is there some mix of objectives that's better for rough terrain? That was a question that came up. And sometimes there are ways that you can, a good example is, can you tell it to not be, to be stable? Can you tell it to not break itself while minimizing energy cost? And a good way to sort of not break yourself is you can limit things like maximum forces. Put too much force on your legs. Stability is harder. You might think it's just don't fall. But it's very hard to say mathematically, don't fall, in the context of an optimization, believe it or not. Who's heard of like exponential stability, asymptotic stability? Is these concepts that are new to you? Okay, they're new to you guys. That's cool. There are all these definitions of stability out there, but they're either useless or so narrow that they're also useless. So you either can't use them or they're useless. It's normally in terms of optimization, to be a little bit cynical. So to the point where people have jokingly created definitions of stability. One is called the Atkinson stability metric. It was invented at a walking robot conference. And he had seen, Chris Atkinson had seen that all these robots are walking around and sees all these experimenters very closely next to the robot, ready to catch it. So he said that the definition of stability is the distance between the robot and its designer. So anyway, it's a hard thing. So it's a hard thing. So one thing we look at is maybe minimizing risk of falls somehow is a good way to characterize stability. And one way that people talk about this is sort of minimizing deviations from your nominal locomotion or your steady locomotion, right? Maybe the further I am away from the simple walking gait, the more in danger I am. And so maybe these are good ways to go. Who knows? So, but sort of answer this question, we looked at birds. We wanted to look at things that run around on two legs all the time. So this sort of motivates, what do animals care about when they're running around? Maybe they'll give us some kind of clue as to what's useful. So we were specifically looking at something called task-level control objectives. Now, to explain what I mean by that, I drew a technical schematic, so I want you to follow me here, okay? Here you have this cartoon ostrich, and it has to care about all sorts of things when it's running around. It has to care about energy costs. It has to go at a speed, maybe, to get away from being eaten by some whatever eats ostriches. Not injuring itself so it falls down and dies. Doesn't fall down and get eaten. Those sorts of things. The question is, how does it juggle these objectives? Hence the elaborate metaphor of juggling ostriches. And what are their priorities? What comes first in terms of all these control objectives? And this is, again, paramount for trying to understand what we should do for optimal control of robots. So, again, I'm talking about birds, but I didn't tell you why. Well, they're cool, all right? All right, let me specifically. So this is a chicken. Basically, it's called a guinea fowl. It's a South African bird, all right? And it's about to run over what it thinks is solid ground, but it's in fact a pothole covered by tissue paper to trick it, all right? And it's going to run over this. It's going to step in the pothole. Oh, gosh, step in the pothole. Up to its knee and catches itself. Very impressive. And I can't do that. I can't run up to a pothole up to my knee and hope to survive. So they're very stable birds. They're impressive birds. Also, birds come in all sorts of shapes and sizes. From quail up to ostrich, this is actually a huge range of species, a 500-fold mass range. I am not 500 times heavier than my colleagues at the lab, for instance. This gives us a broad sample of bipedal locomotion, all right? And also, because each of these birds has such different masses, they typically have different structures to their legs as well. For instance, quail, the tiny creature, have this what we call a very crouched leg posture, very bent, very bent up in its knee up there. Whereas ostriches have this very upright leg posture. Now, why is that? Oh, by the way, when does course end? By the way, 1:45? Yes. 1:45? Okay. I try to get you out here by 2. I'm just kidding. No, that's fine. No, you'll be good. All right. So there's a lot of work showing that maybe these crouchy quail, they crouch so much because then it allows them to sort of crouch onto obstacles and not change their gait very much. That they can sort of just keep trucking along. If something comes in their way, just crouch up, boom, 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 and not have to alter their trajectory very much. Called intrinsic stability was the idea. And also, for ostriches, because they have such a massive body weight, the speculation is that this upright leg posture gives them a big mechanical advantage. That they're using the structure of the leg to support themselves as opposed to actually applying any torques at their knees and various joints. As a result, they don't overload their muscles and can avoid injury. That's another hypothesis that's common in the biological community. And as a result of their different structures, they might have different control priorities because they have different mechanisms. Kind of an interesting idea. So how do we deduce control priorities from these birds? We can't just ask them, unfortunately. I don't think you could ask a person and they would tell you exactly what their control priorities are for locomotion. So how do we tease it out? Well, one is we do experiments with plannable perturbations. What do I mean? So this would not be good for this because the animal was surprised by something that happened. So maybe it's just reacting like, oh gosh, don't die. So let's not do that. Instead, let's give it an obstacle that it can see and sort of plan for. And that gives an insight as to what it cares about. All right? So it's a plannable perturbation. So yes to that. The other way is that we can predict features of an experiment using optimal control. In optimal control, we know exactly what we care about. We told it in the objective of the optimal control problem. That's the thing you need to care about most. And for that, we use trajectory optimization. I think I showed you before. But it's hard to do anything with that if you don't have some kind of simulation or math model to work with. So it became my job to come up with a mathematical model of birds across species from quails to ostrich. So remember this spring mass model? That was going to be the basis for what of our mathematical model of the birds. So specifically, so we started. It has these, it has this very. When you look at the running ground reaction forces of it, you might recall it has this symmetric ground reaction force hump profile when it's running. The problem is that birds actually have a sort of asymmetric ground reaction force pattern with this extra, impulse right here. So we had to explain that in our model. So I actually had to spend some time coming with a model that properly represents birds across species. So I took this simple, very passive model with no actuators, no nothing, and it was just a spring and a point mass. And I added an actuator that sort of just pushes on one side of the spring, kind of like you're pumping a pogo stick or something. And I added a damper that does some viscous dissipation in the leg. So there's energy lost and energy you can put back in via an actuator. Now, how do you use that actuator? How do you control it? Well, optimal control, of course. So I control the extension of this actuator here, which could be some profile over time. It could be anything. And I want to try to find the minimum work trajectory, basically the most energy efficient, mechanically energy efficient control policy for this model, for this actuator. And for that, I used multiple shooting methods this particular time. And when you run it, it kind of smooths out this profile, boom, 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 and basically comes up with a solution which is, don't do anything with your actuator until you're about to take off the ground and then push off in this smooth fashion. And the more dissipation you have in your leg, the more you have to push off in order to keep running. No surprise there. Put a pin in this for later, okay? So what does it look like in this sort of simulation? I had this thing pushing off with a spring. Now, it looks a little extreme in how it's kicking, but keep in mind birds have 2 legs, not 1. And that leg in this model is massless, so it costs nothing to throw it forward at this speed. But when you look at the ground reaction forces, boom, you start to get this little asymmetry popping out. How nice. I have a model that with work optimal control gives me something that kind of looks like the birds. So I actually did something a little bit more quantitative, though. I actually took real bird data and tried to see how close it matched to birds running, to actual bird locomotion. So this is our experimental data we get to compare against. This is a runway from left to right. And off on the left here, there's a tiny little bird, guinea fowl. His name's Greg. He was our favorite bird because he liked to run. All right. So we're gonna clap at him, and he's gonna run. Okay, across this runway. Boom, 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 boom. Yeah. All right. And in the ground, there are force plates that measure the ground reaction force of the bird, and we have it marked up with motion capture markers, and we have Qualisys cameras all around the setup, so we actually have some motion capture data of it, which is good. So we did this across all 5 of those species I showed, from quail to pheasants to guinea fowls to turkeys to ostriches, which gave us all these sort of various versions of ground reaction forces. We just changed the mechanical parameters of these two, of the spring and the damper, and when we do that, we get a mathematical model, these thick lines here, that match quite well with all these birds across species. We were very pleased about that. As a math model, we can now use this to analyze obstacle experiments. So that was all for steady locomotion. So now we want to look at what happens when we have these plannable obstacles. So let's look at an obstacle experiment. So we have the same runway. And this is a turkey running across the runway. And like I said, he's not really challenged by anything so far as just trying to go one direction. So we wanted to try to test how much do they prioritize various aspects of its control, such as maybe how close does it want to be to its sort of steady nominal gait when you give it a perturbation, a plannable perturbation, specifically, boom, an obstacle right in the middle of the runway. How does it handle it? And the question for us was, how is it going to handle jumping on the obstacle? What's it going to do? How much is it going to want to crouch and keep its sort of locomotion center of mass steady versus how much, that's something we think the quail will be able to do because it's so crouchy, which is not the technical term, by the way. Whereas, in contrast, how much does it want to just vault on the obstacle and keep sort of its leg posture the same? Something we think that would prioritize muscle loading, and that's what we think the ostrich might do. And this gives us some insight as to relatively how much each of these species cares about being steady versus not loading their muscles. So where on the spectrum do all these creatures fall? And how does it change across species? So we can do this across all 5 species, and we also jack up the obstacle height, which the birds can handle just fine, which is nice. So what happens? So we found that all the birds' behavior was the same, normalized to their size. They did not care. Didn't care if they were crouchy birds, upright birds. They would all vault about 70%. They would basically do a sort of a 70-30 split, where they would do 70% vaulting, 30% crouching to get over those obstacles. Across all these species, across all the obstacle sizes, too. So we did all these sort of fancy plots, plotting out what the ground reactions forces were. We noted that across all these 5 species, they also had very similar maximum forces, which we thought was interesting. Maybe that's a nice constraint for not overloading their muscles. And their behavior changed smoothly with the size of the obstacle. So it was very consistent. And further, we also noticed that when they dismount the obstacle, even though they probably could have returned back to their steady gait instantly with the capability that they had, they took an extra step to do it. It would accelerate when it comes off the obstacle and then recover back to a steady gait on the next step. So a 2-step recovery. And this is something that I wanted to investigate why using this model I just made. I can put that in a simulation and say, hey, why would that be? What's the cost of recovering with 1 step instead of 2? And basically we found that if you give a 2nd step to recovery, it allows you to run with less maximum force, prioritize not being injured, and also significantly less energy cost to the locomotion. So from this, we sort of implied that if we look at all of our task level control objectives, we did not sense that we did not detect in any of these creatures that has the ability to crouch better than any other, that any of them seemed to care at all about minimizing their steady gait deviations more than any other species. They all cared about it just the same, in spite of their varied ability to crouch. So we did not detect any evidence that they care about minimizing deviations from your steady gait. And leg safety, that's something that we can plop a simple constraint on. Don't exceed this force when you're running. That's bad. And that only leaves one thing in the objective that you're minimizing, which is energy cost, which is what we've been doing. Just because of simple robotics-y reasons that we're trying to minimize energy cost. And we can slap constraints on not breaking our legs. That's something we care about in robots, too. So kind of the takeaway is that maybe animals and robots aren't so different in terms of how we'd prefer robots to be controlled. Don't waste any energy. Don't break yourself. That's it. It could be that simple. So we published this in a biology journal. And the reason that the biologists thought it was particularly interesting is that all these different bird species, boom, 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 have one common ancestor. The closest common ancestor are theropod dinosaurs. So you can either conclude that independently, all these birds evolved the same control priorities, or they all had similar control priorities with their common ancestor, i.e. dinosaurs. So implying that maybe the most parsimonious explanation is that we know something about how dinosaurs move. So anyway, there's also other research that I did in terms of trying to adding mass to the legs and what the implications were, and we were able to predict the change between walking and running. We don't have time for that today, but it's ongoing work right now. And we used this model for other kinds of studies where we tried to figure out how the creature was able to, how the guinea fowl was able to handle these weird pothole obstacles using a robot model of a pothole obstacle. Also, I did this fun study, which was about that model going to have to file its taxes on time. It's called tax day. Anyway, that's later, some other future thing. But also, we wanted to be able to see if we could predict how these animals run on soft ground, things like sand and stuff. So I got to do some experiments. That's Greg. I'm not Greg. And so we had to have it run in like a sandbox, which was fun, which I got to clap and get the bird to go. And we got to have it run over packing foam as well, which required a different technique of motivation, with shaking a box of nails. This plastic bags were good at motivating it as well, and some control trials because they all work so well over solid ground. So anyway, we did lots of experiments with birds, and those are ongoing. And just a preview here, we did do some experiments with this robot that I'm not going to show that are very similar. So anyway, moving on to sort of so the question was, how do you run on soft ground? And that sort of motivated this other study of what happens when the dynamics of the ground beneath you begin to change. And so this idea of terrain-aware locomotion. So our goal was eventually to get bipedal robots on natural terrain, right? Out in the real world. That'd be nice. And we got the Atrius robot at some point. We took it out to the park, and we had to walk up and down hills. In case you're wondering, that big structure is a big slack line, so that would catch the robot just before it hit the ground, so we wouldn't destroy my PhD research. That's a good constraint to have. Don't destroy your research. So, but other than that, it's completely it's holding up its own weight and everything. It's just controlling on its own. And also, the next year, Boston Dynamics put out this awesome video of the robot tromping around in the snow. Really cool. But it's still very uncommon to get bipeds out in the real world on actual natural terrain, not in the laboratory on concrete floors. That's for good reason. And also, I would posit that they're reacting to the terrain as a disturbance. They're not adapting to the terrain and changing the control policy to accommodate it. I know that's the case with this robot because we programmed it. I can only suspect, based on how this is moving, that it's treating everything like it's the disturbance to its body. So, because we don't know what Boston Dynamics does, but I have my suspicions. So, I'm saying they're probably not aware of the physics and mechanics of the terrain that it's walking on. So that was kind of the idea of this project. Make it aware of the terrain. Specifically something like granular media, which is something crazy like sand. It's actually extremely complex in its physics. And the goal of this project was, can I basically create models of terrain that fit inside the optimization in a computationally tractable way such that I can actually come up with optimal control? I actually have some prior experience with this by accident. This is the Atrius robot basically cut in half. This is just one leg. It's going to be bouncing up and down. And I had, for some reason, the bright idea to have it bounce up and down and then put it on a box of rocks. That's just pebbles, so granular material. All right? And I expected it to just do one jump in and out on top of the box and out, just to see what would happen. So we have a jump. It jumps and actually plunges down to the bottom of the box for some reason. I didn't anticipate that, and I'm panicking. That it was going to break the robot, but it didn't. But I think I handled it with aplomb. All things considered. But anyway, the point was, I didn't expect it to jump down to the bottom of the box. And you're not supposed to surprise your control designer, with dynamics that are unmodeled. That's not ideal, okay? So that's what kind of the benchmark for this project was. Like, can I start to incorporate the model of some weird material like sand into the control designer so you don't get that precious space that I made? So here's a simple jumping robot, very small, about yay big. And it's just jumping up and down. It's got a linear actuator, which pushes on the thrust rod, which pushes on this spring, which pushes on its foot, which basically allows it to sort of just like jump itself. And what it does is we command it to actually jump to a particular jump height. We say jump to that height, jump. Okay? That's the benchmark we have. We just like, can we make a robot walk with two legs? We're saying, can we make a robot jump to a very particular height for minimum energy cost? So this is what it looks like. We command this particular motor position, and we model this robot, which is pretty simple. I also model the control loop for the motors, et cetera. And it creates this big optimization problem where I say you jump optimally, meaning for minimum energy cost up to a certain height. So it creates this big optimization problem, which you've seen a couple times now, except now it's for jumping. So now it's going to execute this sort of motor maneuver and make it jump here. So just to show that we can make it jump. And we can tell it exactly how high we want it to jump. So we do it a whole bunch of times where we command different jump heights and see how well it performs in terms of hitting that exact jump height. And so a perfect performance would be 45-degree line, right? So we do this with just a simple model of the robot, and we just do a bunch of jumps, and it sort of follows the right curvature. There's some modeling errors, so we don't get things exactly right. But you can see that we get it along that line. We tell it to go about 10 centimeters high. Again, tiny robot. And it gets roughly close to it. So that's what you just saw. But now we're going to add in granular materials. Particularly, these are poppy seeds. And yes, poppy seeds as in bagels. And the reason we use poppy seeds is because when sand gets in your robot, you tend not to have a good day with your robot. Poppy seeds, when they get in, they just kind of grind into dust that smells like poppy seeds. So it's smelly, but doesn't hurt your robot. Okay? So the trick they use in the granular materials world. Also, poppy seeds are cheaper than buying some other materials, believe it or not. And also, we have this big bed of material where we blow air underneath. So in between every experiment, we completely reset the material so it's all flat and nicely sort of aerated in between experiments, so it's all fresh start, so we don't compact them between experiments. So it's a neat little trick that we use. So now we take that same strategy that you just saw, that thing that just made it jump to whatever 9 centimeters in the air. We're going to put it on poppy seeds and see how it does, and you're going to see it's going to suck. Okay, all right. In fact, that's the jump you just saw, right there. It's supposed to go that high. It jumped that high, so it sucked, right? And that's not surprising. It's jumping on something soft. But you might say, Christian, why are you overthinking this problem? If you want to jump higher, why not just use this strategy here and hope that you end up where you want it to be? Well, I'm glad you asked that. It's a great question. Thank you. So let's do just that. Let's take that strategy up there and see how well it performs. Can it compensate for how givey the material is? So we tell it to jump, and it does even worse. Isn't that interesting? I was completely unfazed by this result, as you might imagine. It's kind of surprising, right? Basically, there's something weird. There's like a mismatch here for some reason. You can't just arbitrarily say, jump higher. It doesn't do it. Okay? So what we have to do is model the material and inform our control policy as a consequence, all right? So, and there are ways of modeling granular material like sand, and none of them are perfect, okay? They're very interesting. There's something called DEM, the discrete element methods, which is basically simulating every single particle of sand interacting with every other one. And that can take hours or days to compute a single maneuver, let alone all the different times you want to go through an optimal control situation. So it would probably take years to use that in optimal control. There's also something called resistive force theory, which works really nice for slower maneuvers, but for something like legged locomotion where you're jamming a foot into the ground, that actually takes it into a regime where these methods don't really work well. So we have to come up with some other way, some other physics-based way to come up with a model of granular material. So the first thing we tried was this jamming cone model. Basically, that when you jam your foot into the ground, you can take a look at how all the grains are behaving beneath the foot, and they all sort of jam up in this very conical geometry. That as you push deeper into the material, this cone starts to form. It kind of goes as you push into it. So we came up with this sort of jamming cone model based upon that geometry and the amount of grains that are contained within it, and it gives us this. And it gives us these terms that are based upon the area of this jammed cone and the volume of this jammed cone as they change over time, which correlates, by the way, to hydrostatic forces and hydrodynamic forces really easily. And the nice thing is that this is a nice simple equation. And that would go into our optimal control methods. So we want to see if this would work as a first guess. And the nice thing is it's all expressed in closed form. So we can use direct collocation and put all these equations in, just like we would, like something like the equations of motion of the robot, which is nice. So we can put that into our optimal control method, tell it to re-optimize, saying here's the material. It only, by the way, all the parameters, we don't tune up the parameters. They just like size of the grains and things we know a priori. And you jumps much better, which is good. So if you go back to the same old plot, there's the results from before. These red dots show where we're at now. Hey, we can now pretty accurately predict how we're going to jump. We tell it to jump, and it says how high. How about that? So that's what you just saw right there. And we also noticed that we looked at the strategies for how the motor was moving. How it jumped on granular material was just fundamentally different than how it worked on solid ground. On solid ground, it would kind of like take its time, it would back up the motor, and then sort of lazily push energy in. For soft ground, it had no time for such foolishness. It just jammed in. which might explain why when we said, hey, just jump higher, it just was fundamentally incongruous for how to jump on granular material. Right? So that might explain why it did worse when we tried to jump higher. So we have this is the first time anyone's done any locomotion that plans through a deforming terrain for a legged machine. That was the first time they did it. That was the first try, though. I mean, but you're probably saying, Christian, what if you don't know you're on poppy seeds? What if you don't know you're on sand at all? What if you're on a trampoline? You know, when you're walking around, you don't necessarily have a model in your head of exactly what this carpet's made out of. And you'd be right. Great point. Thanks for bringing it up. So, what's more interesting to me is if you learn the substrate from experience. That every time you step on it, you're like, oh, that's a little weird. Let me figure out how that works, and I will adapt my control accordingly. So let's take this, what was a granular material model, and replace it with something more general, particularly a Gaussian process regression of terrain data. So that's like a machine learning technique. Basically, it just assembles a model based upon the data it experiences. So and it sounds, maybe if it sounds complicated to you guys, I don't know if it does or not. It's just a bunch of exponentials all in a row. If you actually look at what a Gaussian process looks like as a function, it's nothing too crazy. I mean, there's math behind it, but it's nothing too bonkers. So here's what we did. What we did was we took the jumper here, and we told it was on rigid ground, and told it to jump. And then it's going to jump. It's going to do terribly. But it's going to take data from the forces it experienced and build a model for how that terrain behaved. And then it's going to take that new model, incorporate it into its optimal control method, tell it to jump again to try to get that height. Hopefully it does a little bit better, but it takes that information and updates the model. So, and it's going to do that again and again, and you're going to see it jump. I added the dings. So yeah, you can see after a couple jumps, so it undershoots. It overshoots a little bit, but then it sort of trims it down. And again, it's not learning how to jump. It's learning what it's jumping on and changing its result accordingly. So as a result, we were learning what we were jumping on. That's pretty cool. And the reason this is really nice as well is because we can do more than just jumping. We can use this motion planning for all kinds of different methods, all right? For all kinds of different maneuvers. Because the constraints in the optimization are very customizable. So instead of, say, jumping, and then when it lands, it does this like boingy, 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 boingy-ness, keeps bouncing. What if we say we didn't want that? You know, we can say, yeah, let's add another constraint to make it just stick the landing. So like this, like a gymnast, right? That's Michaela Maroney at the 2012 Olympics, I think. So let's add that as a constraint. So now when it hits the ground, it has to just damp out all the oscillations immediately. Cool. Okay. We just changed the constraints, and it did that. And two things I want to point out about this. We didn't tell it to engage some controller when it hit the ground that says, OK, get rid of the oscillations quick. We planned this out all in advance. And this is how it responded. And number two, when Michaela Maroney stuck the landing at the Olympics here, there was actually a judge in the background who had a very particular reaction that I feel like I can sort of identify with in this particular case. So anyway, so moving on then. So finally, so we'll wrap up here. Is this Atrius robot, this very unique-looking machine, all right, which is about moving on all kinds of different terrain, all right, and also in an agile and robust way. So if you've seen these robots, there actually were 3 of them. We built 3 of them at Oregon State University. We kept one. We sent one to Jesse Grizzle at University of Michigan, one to Hart McGuire at Carnegie Mellon. So if you've seen them around, they're all the same, but we made multiple of them. Now, Atrius is actually designed, unlike a lot of other robots, it was designed to be as close to this spring mass model as we can mechanically make a real machine that could walk out in the real world. So it turns into this sort of like 4-bar linkage design. We had all these different iterations, which got us to this design. And by the way, and that's the reason we named it that way, because Atrius stands for assume the robot is a sphere. We want to be able to assume the robot is this very simple machine, this very simple model. And that gave us some insight into how to control it. So how the heck does it work? It has these 4-bar linkage legs. It can swing around, and this is its workspace when it swings. It can crouch up its legs like this. Further, when you lock the motors in place, when you tell it to resist any motion, and you push on it with a force, it has these leaf springs here that when you push on them, they deflect. So it actually has physical springs in there that give that spring mass dynamics. All right? And just so you can see what it looks like, we lock the motors in place physically with a mechanical stop, and we drop the robot on the ground. So remember when Asimo kind of just fell? It was like a rock. When we drop our robot, it's like a big spring. So very compliant, very flexible. All right. So we developed this controller, okay? And I don't have a lot of time to go into a lot of specifics, but I'll draw in things that we learned from some previous parts of the experiment. So we broke it down into a couple of component controllers, like keep the torso upright, where do we put our foot, how much energy do we put into our robot. And the way that we came up with these controllers is we would do optimizations, very small optimizations for these very simple models that we made the robot a lot like. For instance, we took this spring mass model of the robot, which you remember from various stuff in the previous lecture, and we'd give it little shoves and ask an optimization to say, hey, where was the optimal place to put your foot so that you recover in one step? And it gave us this sort of behavior where the more you push it, it would change this angle linearly. So we're like, OK, well, why don't we make a linear relationship between our sort of error in velocity and that angle? Let's just do that. OK, that's part of our controller. And you might recall, that's what we did with that Durus robot way back in the day. I asked you to put a pin in that. I hope you did. So in practice, we tune up that controller, that slope of that line, by disturbing the robot in a fun way, but in this case with dodgeballs. We try to, and eventually, we take down the robot. You might wonder why. It's because we hit the emergency stop. So that's how you do it. So anyway, that's how you practically tune up a machine, right? So so we kind of went from stepping in place and and to give it bigger disturbances, we took the biggest guy in the lab. We told him to kick the robot. Just give it a good sort of shove with his leg. We also had some excellent simulation tools. We didn't have to try all this on the machine first, so you can see a comparison here between the simulation, where I drew my friend Mikhail in paint, which took more time than I care to say. But it was very good sort of simulation agreeance here. So further, we had this problem of putting energy into the system, because the robot's losing energy all the time. Even though it's a spring mass robot, it's supposed to be this very efficient thing with just a mass and a spring, but it's a real system. It has losses, and sometimes you have to accelerate, put in more energy. And so how do we go about that? Well, remember that? Remember this bird model, where I took that spring mass model and I would push off at the very end of my stance phase? I asked you to put a pin in that. That's what we did here. We would control the length of our sort of motor of that equivalent motor. So you remember sort of this little visual here. We'd push off at the end of the stance phase, boom, like that. So for the Atrius robot, we have control over what is the nominal leg length of this robot, and we tell that to push off near the end of the stance phase, depending upon how much energy we need. In practice, we tell it to do that, but it actually does that because there's back drive. So we took this experiment of the robot where we told it to accelerate to get up to, it doesn't look super fast from this particular angle, but it's actually the fastest any bipedal robot has ever gone to this point, which is 2.7 meters a second. But I also animated the leg length over time after each step. And you can start to see, as you're going faster, this area I'm drawing under the curve of this push-off is going to get bigger and bigger and bigger. Okay, that's the leg length we're commanding for the machine as we go faster and faster. You'll note there's some asymmetry. I'll talk about that in just a quick second. But the faster we go, generally the more we're going to push off, and until we eventually want to stop. Then we start stopping like as fast as we go. Then we start. There you go. And it starts kind of decaying like that. It's hard to get an exact correlation, but but that's how it's commanding its locomotions, by pushing off more or less at the end of that stance phase. So it's also nice because it very naturally handles obstacles. This robot has no cameras. We just tell it to go. And if it stumbles on something, it tries not to fall down. And it notices when, and this is my favorite experiment. So it kind of catches itself on its toe. Right there. I'll zoom in. Right on the edge. But it kind of recovers, puts more energy into the system because it realizes it's lost energy from the trip, and just keeps walking. So, yeah, we're very pleased with that. And I think that my advisor was most proud when we got the robot to start walking, and we just told it to go faster until the point where it actually hit a running gait, meaning it took off the ground. It's hard to tell from the video, but there's actually these, we measured the forces on board the robot, and this is the points where it's off the ground. And so we didn't have a separate controller for walking and running. It just started to run when we told it to go faster, which is actually a first thing that anyone's done with a robot like this. So, but probably the most scary of all is we had to do a demonstration in front at the Dark Robotics Challenge.
Springs is that when it's going, or when Icarus is walking over these obstacles,
because anything can go wrong with a robot demonstration.
Absorb the sudden impact
But we
of these
actually sort
obstacles.
of we did this big live demo where we had it walk over obstacles and had it run in front of a live audience. And that was really fun and rewarding for all of us. And this old energy cost plot, Atrius is not too bad. 1.3. I mean, the whole thing's a giant spring. I guess, we expect, as a result to recover a lot of energy, not lose too much. But still, if for a practical machine, not too much worse than the Durst robot, in spite of the fact that we could do a lot more with it. We can have it walk and run at different speeds and things like that. So what's next? So I'm here at Florida State now. This is my first year. And I have procured a robot that is, so I'm starting my own lab now. And I have sort of like this overarching hypothesis that if you build a robot with passive dynamics that are like these spring mass models, okay, and then you do optimization on objectives from animal locomotion, in this case like energy cost, and so you do optimization on that, you should get locomotion that's like an animal. Basically, I want to demonstrate the idea that, hey, when a robot is running its best, it's running like an animal. Not because we told it to run like an animal, but because it's running its best. So and here's some preliminary data that we took of Atrius walking, of the ground reaction forces of the robot relative to some schmo, i.e. me, walking over a force plate. So here, the dynamics of how the robot is walking is actually quite similar to how the dynamics of a person in these cases. And the way I want to do this next is with a brand new robot. It's called Cassie. It actually looks a lot like an ostrich, but really it's designed for function. It was built by a spin-off company that grew out of the lab I did my PhD research in, and they sell robots that are fully functional, that are basically like Atrius, except they can do three things. One, they can stand still. Atrius could not stand still, which was interesting. It actually had to step in place. It had only tiny little point feet, so it couldn't stand in place. It had no actuators to those feet. This one has tiny little feet that you can actually apply torques at, so it can stand still. Two, it can turn. Atrius only had 6 motors, so it didn't have the actuation authority to be able to turn. It actually only could sort of walk back and forth at different speeds and sidestep, but it couldn't turn. This one can turn. And most importantly, this one can fall down and not break. So I'll be getting this robot in about 2 months in my laboratory to test this exact hypothesis. So yeah. So, and by the way, they're showing it walking around, but we know that the robot can move pretty freaking fast. So that's what I'm going to be working on in the near future. So anyway, so I think that bipedal robot that I can make it run like a bird in natural terrain. That's what I want to get to do. So and finally, I just want to point out, this whole thing was a very interdisciplinary exercise. We went from robots and taking things we learned from robots and in order to inspire questions about birds, take things we learned about birds and apply them to this robot, etc. This is very interdisciplinary, which is pretty neat. But also, I see these all as under the umbrella of optimization. And I think that there's a grand question about how optimization can help all these different fields, because optimization, just cool. So with that, I want to thank all my colleagues over the years who helped me so much with all this research, and I love to take your guys' questions. So, thanks. If not, you can go. I know I'm about 2 minutes over. Sorry about that. Yeah. So those were our 2 free parameters that we would tune to the actual biological data. So if you had a given damper and you did optimal control, it would come up with some force profile, right? And you change that damper, that force profile changes a little bit. So you just change that force profile, that damper a little bit, it gets something that looks exactly like the birds. But we only have 2 parameters to fit with, and the whole rest of the curve just matches the birds nicely. Got it? Yeah.
On an ostrich, it's knee bent backwards, and if a human is bent moderate, so does it make any difference for a robot?
So the first thing I'm professionally obliged to tell you is that you're right to point that out. That is actually not its knee. It is its ankle. its knee. Isn't that neat? So that's its ankle, and that whole thing is its foot. Its knee is up here. Isn't that interesting? So, but that's a thing we come across all the time. Why is that important, and why? And one of my colleagues did a study on the on the kinematics of an impact to something that has say a backward configuration versus a forward configuration. And the backward configuration seems to handle impact better, and that they don't travel up the body as much. And that's one hypothesis. When it comes to my research, I tend to care about that detail a little less because I'm abstracting the whole thing into just this mass and a spring. That overall, the overall body dynamics tend to be similar. So, that answer your question? Thank you.
Yeah, same thing.
That's great. It's a good question.
So the metric you use to compare the robot's efficiency for walking versus a human, do you guys have like that metric for like birds? Because you're analyzing them mostly. So is it like similar to that of humans? And then also, what about, I guess, the natural walking cost makes it so hard to reach with the machinery itself?
So humans, I believe, have a better cost of transport than birds. That's a factoid I should have off the top of my head, but I'm embarrassed. People do analyze them at different speeds, because it also matters. The speed matters, by the way. You know,
Right.
that as cost of transport you're going. And second question was about why robots. A big part of the robots, I have to admit, is the design. That we're just not. I mean, muscles are great at a lot of stuff. They put out a lot of force without a lot of stuff. They don't need giant gear reductions to do it. But muscles also have a weakness in that loading up a muscle costs energy. Theoretically, there's no reason force should cost energy, but in muscles they do. So there are people who study ways to improve the human body by basically slapping mechanisms on when they're walking onto their calves that sort of support them during this phase of just force. So muscles rock. It's very hard to get a large gear reduction on motors to get the forces that you need. So there's mechanics. But really, for me, even if we had, even if you made a muscle-driven robot, it is hard to control. I mean, we almost design motors that we put in more current, we get more torque out. They have this very well-described behavior, and muscles are complicated. Does that make sense?
Yeah. Because I figure like if you have a human foot, you're walking through the terrain, your muscles in your foot are going to help you maintain like your balance or your speed. I just didn't know that.
No, like there's questions of transmission. How do you get forces down there? I mean, the easiest way that people do is with hydraulics. I mean, Boston Dynamics does hydraulics for all their machines, and I can't blame them because that's how you get a bunch of force out down to the bottom of your foot really easily. But hydraulics are not the most efficient things in the world. Anything else? All right. All right. Between the motors and the legs, I mean, we have in Atrius you have a harmonic drive, which is our transmission, and you have most importantly you have a spring between the motor and the leg. That's really important for the function of the robot. Yeah, and like these methods that we use to make Atrius go, they wouldn't work for a robot without springs. They wouldn't. I mean, so we had to design it special for this machine. We don't change the mechanical stiffness of the joint, no. The closest thing we do to that is one of the things of our controller is that we have very loose PD gains on our controller. Does anyone know who knows what a proportional derivative controller is? PD? For PD? Okay. Yeah, PD. Yeah. So I mean, it's basically it controls something like it's a spring damper, right? Yeah. So if you have a spring damper in series with another spring damper, you get series concatenation of springs, and the spring is softer. But we don't intentionally control it to be a particular stiffness. We just say that's the stiffness. Let's just roll with it. But that's something that that's hotly debated in our field. Do you want to change the stiffness of your spring? Because humans, we change the stiffness of our muscle all the time, right? I can contract my muscle. I try not to be embarrassed by doing it in front of you people. But you can really stiffen your arm up. If it's just the spring, you can't do that. But it's hotly debated how necessary it is, and also how you would do it. It's hard, but I'm impressed by the people who try. Yeah. Anything else? All right, I really appreciate you guys coming. Then let me go over about, oh gosh, 7 minutes. That's like terrible. All right. Yeah, cool. We'll see you guys later. You want to take a look? The talk will be online. How about that? This thing is about a gigabyte. Sorry, the size of file, a gigabyte large. Okay. Yeah, so I pretty much